Başlayabiliriz Oğuzhan Hocam.
Neyse ben başlayayım. Sevgili katılımcılar, sevgili akademisyenler ve meslektaşlarım. Bugün Dünya Çarpışma Rotası'nda bir asteroid çarpışması sırasında ne olur başlıklı oturumumuz Profesör Doktor Thomas Kenkmann tarafından Freiburg Üniversitesi'nin katılımıyla gerçekleştirilecek. Bugünkü konuşmanın amacı bizler jeologlar olarak Güneş sistemine baktığımızda birçok gezegen ve gezegensel cisimler üzerinde en temel jeolojik süreçlerden biri olan çarpışma kraterlerini görüyoruz. Bu çarpışma kraterleri tabii ki dünyada da kozmik bombardıman sırasında gerçekleşiyor. Fakat böyle bir çarpışma sırasında tam olarak neler oluyor? Bunları anlamak ve bunun oluşturduğu morfolojik etkenleri tanımlamak adına bu oturumu gerçekleştiriyoruz. Aynı zamanda böyle bir çarpışma sırasında ne gibi sonuçlar bekleyebiliriz? Veya günümüzde çarpışma riski ne kadar yüksek? Bunu anlamlandırmamız gerekiyor. Bu konuşmada farklı kraterler formlarının nasıl oluştuğunu ve bir çarpmanın dinamik oluşumunu açıklamayı hedefleyerek aynı zamanda sorulara cevap vermeyi amaçlıyor. Kısaca Thomas Kenkmann'ın CV'sinden bahsedeyim. Thomas Kenkmann, Köln Üniversitesi'nde jeoloji ve paleontoloji eğitimini aldı ve 1997 yılında Berlin Hür Üniversitesi'nde doktora tezini tamamladı. Doktora öğrencisi olarak GFZ, Geofashion Centrum Potsdam'da, Berlin yakınında Almanya'da çalıştı ve akabinde doktora öğrencisiliğini bitirdikten sonra yardımcı doçent olarak Berlin Doğa Tarihi Müzesi'nde çalışmaya başladı. 2010 yılından bu yana da Almanya'da Freiburg Üniversitesi'nde jeoloji ve yapısal jeoloji profesörü olarak görevine devam etmekte. Thomas Kenkmann ve çalışma grubu birçok uydu görüntülerinden mikrometre ölçeğine kadar değişen yapılar üzerinde dünyada ve diğer gezegenlerde çarpışma kraterlerinin yapısını ve deformasyonunu araştırmayı amaçlamakta. Thomas dünya çapında 40'tan fazla çarpma krateri üzerinde çalışmış tutkulu bir saha jeoloğu, bunu direkt söyleyebilirim. Öğrencisi olarak da bunu direkt söyleyebilirim. Ve kendisi sayısız krater keşfine ve kraterlerin doğrulanmasına da katkıda bulunmuş. Aynı zamanda Profesör Kenkmann'la beraber krater deformasyonları deneyleri farklı kaya türleri üzerinde gerçekleştiriliyor ve farklı multidisipliner çalışmalarla birlikte, enstitülerin katılımıyla birlikte bu araştırmalar yürütülüyor. Kendisinin katkılarından dolayı, çarpışma kraterleri araştırmalarına olan katkılarından dolayı 2018 yılında Meteorological Society tarafından kendisine Barringer madalyası ödülü layık görülüyor. That's all. Thomas, the stage is yours. I think you can start now. Thank you.
Okay. Yeah, thank you, August Kahn, for this kind introduction that I did not understand. But I guess you have said kind things.
You should be sure, yeah.
Okay, so I start my presentation now and would like to thank for the invitation to have the chance to give this presentation in front of the Turkish Chamber of Chamber of Turkish Geoengineers. Yeah, and yeah, the topic might be somewhat unusual for you. Earth on collision course, what happens during an asteroid impact? Among geologists, this topic often sounds still a little bit exotic. Yeah, but I would like to convince you that this is really an important process, and I would like to introduce you to this young research field and what happens during an impact, actually. So I have subdivided my topic here into 4 chapters. The first, let's have a view on the solar system, looking a little bit beyond Earth. We will see a lot of craters there, and then we will talk about projectiles and collision probability. The third topic, what happens during an impact, based on observation on Earth, based on experiments and numerical computation. And finally, what can we do if these sort of things happen. Okay, so let's start with the first topic, yeah? And well, you know, the moon, we see this picture at full moon with naked eyes. You can see the craters, yeah? You see the bright highlands and the dark Mare regions. Yeah, these are flooded, huge impact basins, circular impact basins. And so the moon has suffered tremendous amount of impacts in its history. And actually, if you look at the surface of the moon, it is bombarded everywhere. And we have about 1.5 million craters, larger than 1 kilometer in diameter on the moon's surface. Yeah? This is really a huge amount. And the Earth and the moon, they share one orbit. So the collision rate that has affected the moon has also affected the Earth. The Earth even larger because the Earth is larger and the gravitational cross-section is larger. Yeah? So the lunar surface has been investigated, for instance, in the NASA's Apollo program 69 to 72, and astronauts, they looked at different sites on the moon, collected samples there. They returned 380 kilograms of samples back to Earth. And these samples from the different sites here are the Apollo sites, they could sample different areas which have different crater densities. Yeah? And with this, a very, very important result came up, namely that the collision rate was very, very high at the beginning of the solar system, 4 billion years before today until 3 billion years. That is a period of early and late heavy bombardment. And another result of these missions were that for the last 3 billion years, yeah, until today, we have approximately a constant bombardment rate, which is not zero. Yeah, it is not negligible. Yeah, there is a certain risk still today that impacts can happen. Yeah, if we look on our planetary neighbor on Mars, yeah, Mars is geologically much more active than the moon. Yeah, the moon is geologically inactive, yeah, except for collecting impact craters. Yeah, Mars shows 300,000 impact craters, larger than 1 kilometer. Yeah, so they have different sizes. You see small craters; these are bowl-shaped cavities. You see larger craters with a central mound. You see very oblique impact craters, yeah, which have elliptical shapes. Yeah, so still a very, very high number of craters. Even if we look at the minor bodies in our solar system, yeah, like asteroids or the little moons of Mars, which are also captured asteroids, even those small bodies are punctured by little craters. Yeah? This is a dominant landform. Yeah, and if we go to Mercury, that is the planet approximately. Yeah, it is very similar to the moon. It has craters very similar to the moon, craters of different sizes. Again, the small craters are bowl-shaped cavities. The larger craters have these terraces, a flat floor, and central uplift. And the very large ones have several rings. Yeah, so more or less the same picture. And even if we go in the outer solar system, yeah, to the icy moons, for instance, of Jupiter and Saturn, yeah, we see icy surfaces that are covered by craters. Yeah? So that is really the most important landform in our solar system. Yeah? Actually, there is only one planetary body in the solar system with a solid surface that has no craters on its surface, and that is the Jovian satellite Io. Io is very close to Jupiter, and there are very strong tidal forces. So this Io is the volcanically most active body in the solar system. And there, the resurfacing rate is higher than the impact rate. Yeah? And therefore, we do not find impact craters on its surface at the moment. Yeah? So now looking back at the Earth. So where are the craters on Earth? Well, from space, we don't see them. Yeah? But of course, I wouldn't give this talk today if there wouldn't be some craters on Earth. The status quo at the moment is we have discovered so far 210 confirmed impact structures. And you see them here with the yellow dots, plus 32 so-called secondary craters. These are not craters formed by an incoming asteroid, but they formed from the product of a large impact that ejected some boulders, and those boulders produce craters again. Okay, so you see some of the spots are tiny, while others are bigger. The smallest craters we have on Earth are just a decameter in diameter. These are these little holes here. This one, Caracas in Peru, has recently been formed in 2007, or Stelitamak in Russia has been formed in 1990. Yeah? So these are just some 10 to 15 meters in diameter. And on the other end of the range, we have this crater here, the Vredefort crater in South Africa. This is this circle here. Can you see my mouse? Yeah, okay. So this crater is actually 250 kilometers in diameter. Yeah? So this is at the upper end. You see that the distribution of craters is uneven. Yeah? There are areas like in Siberia, or in the rainforest of Brazil, or in the rainforest here in Africa, where a very few craters have been formed. They have been discovered so far. This is due to the dense vegetation, the intensity of surveying. Yeah. But this is not the only explanation why we have a concentration. We have a strong concentration, for instance, here in North America, or here in the Baltic area, Baltuscandia, or also here in Australia. These are areas where we have Precambrian rocks exposed. Yeah? So the cosmic exposure time is quite long here. So there is a long time for collecting impact craters with time. The erosion rates are very small here in these stable cratonic areas. Yeah, that explains the higher densities. And of course, 2/3 of the Earth are covered by oceans, and we do not see any dots except for this one and a few others that are located in the oceans. Well, there is one disturbance here in the South Pacific Ocean. That is the Altanian Disturbance. It has not formed a real crater. And you have to consider, on one hand side, that the oceanic crust on average is much younger than the continental crust, only some 60 million years on average, yeah, before it. And you know the mobility of oceanic lithosphere that is being subducted, yeah. And of course, the water column, on average 4 kilometer deep oceans, yeah, they are protecting craters to be formed at the ocean floor. Yeah? So it requires about a 1 kilometer sized projectile to form a crater at 4 kilometer water depths in the ocean floor. Yeah, that is another reason why we obviously have a lack of craters in the oceanic basins. Okay, so if you are interested in the current knowledge on what we on the distribution and how these craters look like, we have just recently published a 2-volume atlas of the terrestrial impact structure based on the Tandem X imagery. This is a mission with 2 satellites from which high-resolution digital elevation models could be created, and they are the base of this atlas. And I will show some pictures from this atlas. So if you are interested in that, yeah. Okay, so the Earth is, on Earth, obviously it is a bit more difficult to detect craters as on the Moon, because the Earth is an active planet. We have erosion, we have burial, yeah, we have deformation, plate tectonics, and all these. So this is a discovery history. Yeah, you see the first impact structures have been discovered at the beginning of the last century, but these were usually small craters where meteorites were associated with the small craters. Then in the early 60s, it became clear what are the criteria, what happens during an impact, yeah? What do we have to look for, yeah? And when that was clear, yeah, the discovery curve started to increase exponentially. And yeah, with this curve, yeah, we are at 210 or so. We can also use this curve to extrapolate how many craters we might expect to find in the future. Yeah? If we use this exponential law, yeah, we may come up with a total number of, let's say, 350 craters if we apply this sort of equation that starts in the year 1960s when the criteria were clear. Yeah, we can also use a so-called logistic function. Yeah, this is a double exponential fit curve. Then the total number to be expected is a bit disappointing. That means we could find only some 30, 40 craters, and we have already found the majority of craters. Well, I leave that open for the moment, but the question remains, why is it so complicated on Earth to find impact structures? Well, if we start with a typical cross-section of a complex crater, what a complex crater is, I will explain later on. So let this be the cross-section of a pristine crater with a complex morphology. It has a crater rim. It has an ejector blanket. It has a terraced rim zone, and it has a so-called central uplift. And this is how the structure looks geologically. So when this structure is being buried, yeah, it is no more accessible by surface geological surveying. So it requires geophysics and drilling. Yeah, these are indispensable tools to recognize such a buried crater. Those craters are usually very well preserved, yeah, but they are hard to detect. Yeah, for instance, the famous Chicxulub crater that formed at the KPG boundary, yeah, and that is responsible for the extinction of the dinosaurs and other species. This falls into that class. Yeah? It was later on buried by younger tertiary beds, and it protected the structure on one hand side, which is good, but it also shielded the crater from detection. Yeah. The other way is that this pristine crater structure is being eroded right after formation. Yeah? So then we see some remnants of the crater structure. As a crater is usually bounded by some normal folds, yeah, they are dipping inward. Yeah, these remaining structure is usually somewhat smaller than the original structure. Therefore, we call it the apparent crater, or the apparent crater size, what we are measuring. And we see some relic structure, which is usually a result of different erodibility of the different units. Yeah, quite often we see the remnants of the central uplift peeking out somehow. Yeah. Okay, if we look at the totality of the craters that we have discovered so far, about 73% are somehow exposed, 40% are partly buried, 21% are completely buried, yeah, 44% show a real clear visible crater morphology, 20% is subdued morphology, yeah, and some are completely or partly submerged. Yeah. So to give you some examples from the atlas, this is a structure that has recently been discovered, or some 10 years ago, in China, 1.8 kilometer diameter. This is quite easy to detect. Yeah, you see the mountain ranges here with a typical valley formation with a typical discharge systems here, and you see this clear morphological depression. Yeah, so this is only slightly eroded and clearly visible with the cratering. A somewhat bigger structure, 5 kilometer in diameter here in Australia, Gold Paddock, is already a bit more complicated to detect. Well, what you see is actually a flat plain that is surrounded by this hilly region. Yeah? And it is this slightly elliptical ovoid structure that makes it clear that it is a crater. Yeah, but it is partly buried. In the central portion, it is buried. And you need to drill here in order to get access, for instance, to the central uplift. Yeah. Other craters in a different climate zone, for instance, here, the GO structure in Canada, this is a landscape that is scoured by the last glaciation. You see these typical valleys and landscape formed by glaciation. And in Canada, and also in the Baltic Shield, you often find these more or less circular to irregular features, usually deeper lakes than the other lakes. And this has an island as a remnant of the central uplift. Yeah, so this is partly submerged structure. And this here, a structure in Brazil. This is very nice, but this is eroded. Yeah, this is not the pristine morphology of the crater. What you see is a color here. This is part of the central uplift, but only that part forms a color that is composed of very competent beds. Yeah. So it depends on the erodibility, yeah, of the material. And then we have some craters on Earth where you cannot see anything. Yeah. For instance, here the structure Manson in Iowa, in USA, 35 kilometer. It is completely buried under till, yeah, from the glaciation, last glaciation, and it requires geophysical surveying to see the structure. And of course, you have to probe, you have to sample the structure in order to prove the crater. And still another one here in the Atlantic Ocean, yeah, close to Nova Scotia. Yeah, this is entirely submerged, and it's a huge structure. Yeah. So you see, craters on Earth are partly very difficult to detect. Yeah. And the history is, or it is a post-impact history that makes the discovery so complicated. Yeah. So this is just a theoretical diagram. If this is the impact here, on the y-axis, you either has burial or erosion. After impact, you might expect in some cases that you just have burial, like in the case of Chicxulub. Yeah, then you follow this path. Or if you just have erosion, you might follow the green path. But if you erode too deep, we will see, if you reach, let's say, a threshold depth where any impact-related rocks and shock features disappear, are eroded away. So if you exceed that limit, you won't detect this crater any further. Yeah, and then there are more complex paths. For instance, initial phase of burial followed by a phase of erosion, or vice versa. Initial phase of erosion followed by burial. Yeah, this all is possible. Okay, and that makes it clear that we have not discovered all craters. Yeah, but we are very interested to have at least an estimate how many craters can we expect to find. And for that, we used the production rate of craters that we know from the moon. Yeah? That is the so-called crater production rate, the lunar crater production rate. We adopted it for the Earth, and then we included a mean erosion. Yeah? And that led to a different curve, yeah, in this cumulative plot. And these little triangles are the cumulative plot of the different craters we have detected so far. And you see a quite good match with this curve here, except, yeah, in this part here, this is a good match, but let's say from 6 kilometers downwards, we see that these curves do separate. Yeah? That means here in this diameter range, you have 6 kilometers and smaller, we are missing most of the craters. Yeah? So we are missing, in particular, craters less than 6 kilometers in diameter. And the number from this prognosis here, or from this calculation estimation, is that we are missing approximately 300 craters, yeah? Which is somewhat similar to our approach from the discovery history, a bit more, yeah, but on the similar magnitude. Okay, so this is my first introduction. So now I would like to ask, yeah, what are the projectiles, yeah, that cause these impacts to form? Yeah? And what is the collision probability? Yeah? So for that, we have to look at the sky. Yeah? We have two classes of incoming objects. The less frequent class are the comets. Yeah? We have short period and long period comets. A long period comet here, like Hale-Bopp, yeah, that was observable in 1997, at least in Germany. I remember that they typically have these two tails. Yeah, they develop these tails once they approach the inner solar system. Comets are coming from the outer solar system, yeah, beyond the orbit of Neptune. Long period comets even come from the Oort cloud. So these are both short period and long period comets are mainly composed of ice together with some dust, yeah, dirty snowballs, yeah, sometimes this is this name is given to the comet. Yeah, and we have this sublimation of the ice when those bodies approach the inner solar system. Yeah, and then they produce these tails. Yeah, the more important fraction of projectiles are formed by asteroids and fragments of asteroids. This is one big asteroid here, asteroid Eros, 34 kilometer by 11 by 11 kilometer, so uneven shape. It itself is covered with craters, as you can see here, and the majority of asteroids, they are from the so-called asteroid belt. And the asteroid belt is an orbital range between Mars and Jupiter orbit. Yeah? This is where the majority, hundreds of thousands of asteroids are located in this orbit. Yeah? And you see this is heavily populated and it contains some gaps here. We call them Kirkwood gaps. And once asteroids, for instance, by collision in the asteroid belt, enter these Kirkwood gaps, these gaps, they are in resonance with Jupiter. And so they will be attracted by Jupiter. So these are unstable orbits. Yeah? And once asteroids fall in these Kirkwood gaps, they develop more elliptical orbits. And that means that they also enter the inner solar system and can become near-Earth asteroids. Yeah, so that is one way how we can generate near-Earth asteroids. Yeah, because that is the group of asteroids we are interested in. Yeah, we are interested in those asteroids that cross the Earth's orbit. Yeah. Okay. Yeah, these are called near-Earth asteroids. Yeah, this is just to show you some of the orbits of these near-Earth asteroids. Yeah, that does not mean that every of these near-Earth asteroids necessarily needs to collide with the Earth eventually. Yeah, but those asteroid orbits, they touch the orbit of the Earth or cross the orbit of the Earth. Yeah, to show you the population of near-Earth asteroids, this animation is helpful here. The red dots represent near-Earth asteroids. Here in the center, we have the Sun, then we have Mercury, Venus, Earth orbit, Mars. It starts again. And here we have the Jupiter orbit. The green, these are the main belt asteroids, and the red one are the near-Earth asteroids. Yeah. Just to show you how densely populated the inner solar system is by such asteroids. And this has been, or this became clear at the end of the last century, when different sky surveys started their work to detect such near-Earth asteroids. And this is a very successful discovery history by various surveys. And it shows here in different size classes of asteroids, the number of near-Earth asteroids. For those that are larger than or 1 kilometer and larger, we have detected almost all of them. These are slightly less than 1,000 in number. The number is slightly rising still. Those that are larger than 140 meters, yeah, we have detected here some 10,000, or if we include the larger portion here. And but we still see an exponential increase when it comes to the smaller asteroids. Yeah? And well, so this is yeah, if we make a prognosis for the future, yeah, we can estimate that we have more than 100,000 near-Earth asteroids. Yeah, of course, it is more difficult to detect the smaller ones. Yeah, they have a smaller albedo, they are harder to detect. Yeah? So you see here the discovered asteroids here. This was published here by NASA. The number of those that are larger than 1 kilometer. Yeah. And here, in particular, for the smaller craters, for the smaller objects, yeah, this number should be much, much higher. Okay. So to illustrate that in a different way, this diagram shows the discovered structures here with morphology in brown. Yeah. Of the large craters, we have discovered probably more than 90%. Yeah. 500 to 1,000 meter diameter asteroids, probably some 50% or so, 300 to 500 meters, some 30 to 50%, and of the smaller ones, yeah, we don't know how many will be there. Okay, so this is a very, very important way to also to assess the risk. Yeah, if those objects, those near-Earth asteroids, are being detected, their orbit can be calculated and can be also calculated in the future. So we see when close approaches will take place. Another way to look at the statistics is to watch at the night sky what is incoming. Yeah, what is entering the upper atmosphere. Yeah, of course we see the many shooting stars, and we are always happy when we see a shooting star. Yeah, these are dust particles. Yeah, just a millimeter and less in diameter, and they ionize the atmosphere. Actually, about 100 tons of cosmic particles enter the Earth's upper atmosphere and rain down as dust, yeah? Accumulating to 40,000 tons per year. Yeah, so these incoming small particles are investigated, for instance, by the European Bolide Network, and there are other networks in other countries that control this. Yeah? And of course, we have different periods, like the Perseids, or the Leonids, when showers of small material is entering into the upper atmosphere. The Earth is a protection shield for those tiny particles, no problem with that. Yeah. However, yeah, there is also a measure of larger bodies incoming into the atmosphere and creating infrasound waves, yeah, that can be recorded by a network of infrasound wave stations. Yeah, and this is a map of incoming bolides. None of them have actually reached the surface. Yeah, but these are quite significant objects. Yeah, the smallest of these objects have approximately diameters of 1 meter or 2, and you can see the kinetic energy. Yeah, the mass times the velocity squared divided by 2. Yeah, this is the kinetic energy of this incoming material. And the largest event that was recorded, yeah, in this time period is this one. That is the Chelyabinsk event, and that has caused significant damage, as you will see later on. And you may remember it. It created an airburst that was quite significant, and the blast wave led to some destruction in the area of Chelyabinsk. Yeah. So here we have quite a good measure of the statistics of incoming material. Yeah, and of course, small materials is entering the Earth's atmosphere more frequently, but than larger material. But the larger material also comes. Yeah, and but for the smaller materials, yeah, meter to decameter in diameter, the Earth's atmosphere is still protection shield. That is the very good news. Yeah, and you can see how the protection works. Yeah, this is a film of this bolide, of the Chelyabinsk bolide, entering into the atmosphere. Yeah, so here you can see the fireball. Yeah, it gets brighter than the sun eventually. This is absolutely extreme, and then it fragments and gets strongly decelerated. Yeah, this is the Chelyabinsk fireball, and it released an energy of 500 kilotons TNT equivalent into the atmosphere. Yeah, this is approximately 30 times the energy of the Hiroshima bomb. Yeah, and it created a blast wave. Yeah, a shock wave in the atmosphere. And here you see the isobars of this blast wave, and you see where damage occurred. Some 1,500 people get injured, yeah, and infrastructure was damaged, yeah, glasses were fractured, chimneys broke down, fell down, and but eventually the atmosphere were capable to strongly decelerate this incoming body, yeah. So here you see, this is the altitude, this is a modeling. You see the altitude of the atmosphere, you see the brightness of the body, yeah. So this is a peak of brightness, this is the mass, and here you see the energy deposition. So most of the energy is deposited in the atmosphere, and only a tiny fraction is finally ending up at the surface. Yeah. So this body eventually was so strongly decelerated when it broke apart that it fell down and could be collected as meteorite pieces. Yeah. They fell down with terminal velocity. Yeah. So most of the cosmic velocity, which was initially some 20 kilometers per second, yeah, was decelerated to this terminal velocity. So actually, what is happening when a body come into the atmosphere that is at this threshold size, what the atmosphere can still absorb, then we have this type of scenario. So this would be what we have seen with Chelyabinsk. We create a fireball that gets brighter and brighter, and we create a blast wave. Such an event was also happening during the Tunguska event that was in the early 20th century, in 1906. But if the bodies get bigger and they keep the kinetic energy, yeah, then this point of breakup probably reached the ground, yeah, and then the fireball reached the surface. It creates a strong heat pulse, and of course, the blast wave goes over the land, and at this point, we form a real crater. Yeah. Okay, so let's have a look at the crater events or the airburst events in the last century or in the past 115 years. Yeah. The largest event actually was the Tunguska event, 1908. Yeah. It happened in the taiga of Siberia, and it destroyed a forest in an area of 2,000 square kilometers. If this would have happened in a town, yeah, it could have killed millions of people. Yeah. Another big event happened with an iron meteorite this formed a strewn field of small impact craters. Yeah, so a large number of impact craters. This was possible because this was a high-strength body, iron meteorite, and it created a large number of small craters, 100 small craters, 120 small craters. I've already mentioned Sterlitamak and Caracas, 2 small craters, and the recent Chelyabinsk event. Yeah? So these are the events that happened, that are recorded on Earth in the last century or so. So if we put that into a probability map, yeah? So crater diameter versus probability. Yeah. Sorry, this is partly in German, but I try to translate it. Yeah, we see the Chelyabinsk event here. This statistically, it happens on the order of once per century or once per decade. Yeah. And the larger the structures are getting, the less frequent it happens. Yeah, for instance, a 1 kilometer crater, yeah, a real crater, like the meteor crater in Arizona, forms about one time in 1,000 years. And a crater of, let's say, 25 kilometer diameter, like the Reese Crater in Germany, happens on average once every 1,000,000 years. And the Chicxulub crater, responsible for the KPG boundary, statistically happens approximately every 100 million years. Yeah? And this caused really a global catastrophe. Yeah? And this, the diameter of the craters could be related to projectile diameters. So a Reese crater would be formed by approximately a kilometer-sized projectile, and the Chicxulub crater by about a 10-kilometer projectile. Okay, so that's that was the second chapter here. And now let's come to the core. What really happens during an impact? Yeah. Well, this is a very fast process. And well, if we do geology, we just see the final end product. So like for instance, here in the Nördlinger Reese crater in Germany, yeah, we see a crater 26 kilometer in diameter, yeah, still clearly visible, yeah, but we just see the final end product, and but we want to understand these split-second processes, yeah. So, and that makes it necessary to combine field studies with experimental work plus numerical simulation. Yeah? And I will show you some results of all 3 aspects. Yeah? So let's try to analyze this story with the example of the Reese Crater. Yeah, so this is a cartoon here, but it is based on numerical simulation, yeah, of this process. Yeah. So imagine you have an asteroid of about 1 kilometer in size, a bit larger probably. It impacted at a typical velocity of 20 kilometers per second. You have no deceleration for these size of asteroids due to passage through the atmosphere. And once this bolide is touching ground, yeah, you convert the kinetic energy into various forms of energy, yeah, into heat, into plastic work, and all this, the propagation of this transformation front is the so-called shock front. And this shock front is propagating more or less spherically into the target, that is the ground, and back into the projectile. Yeah. The initial pressures that develop in such a case are in the order of 400 to 500 gigapascal. Gigapascal, to give you a number here, 1 gigapascal is 10 kilobars. That is approximately the pressure that occurs at a depth of 30 kilometers. Yeah? So for a very short period of time, just a split of a second, we reach extreme pressures, yeah, and extreme temperatures. Yeah? The target at the time of impact in southern Germany was composed of limestone here, Jurassic rocks underlain by Triassic rocks, and then we had some basement rocks, granite and gneiss. Yeah, and what happened at first is that we have a very, very high speed current of melted material that that forms so-called distal ejecta tectites and moldabites. Yeah. And then what is happening? The shock front is propagating, of course, into the projectile and into the target hemispherically, yeah, thereby attenuating, of course. So the maximum shock pressure and shock temperature will decrease. You see the isobars here. So this is a limit of 600,000 bars, yeah, 60 gigapascal. Yeah, this is 20 gigapascal. Yeah, and you see how fast this shock front is propagating. Yeah, and of course the asteroid will be strongly compressed. Yeah, and what is happening is that the initial crater is being excavated, and we have the start of the formation of a so-called ejector cone or ejector curtain. And this cavity is growing, yeah, and it is growing because of the processes that are happening in shock waves. Let me briefly give an excursion to shock waves. So what is so unusual with shock waves? Well, shock waves are anomalous with respect to standard seismic waves. They propagate at velocity higher than the speed of sound in that specific media. So a shock wave in air is faster than 300 meters per second, the speed of sound, and the shock wave in a granite is faster than the P wave velocity and S wave velocity in this material. Yeah, and what is very important with shock waves, and different to seismic waves, elastic waves, shock waves set the material they have passed into motion. That means the material that has been passed by a shock wave is following the shock wave, and this actually opens the crater cavity. Yeah. And the material that has been affected by a shock wave looks different afterwards. So some plastic deformation occurs, what we call the shock metamorphism or shock metamorphosis. Yeah. So specific type of shock effects develop. This is different from regional metamorphism. I will show you in a minute. And due to this plastic deformation, the rock is being heated. Yeah? It's being heated due to these processes. Yeah? And depending on the intensity of the shock wave, this can lead to melting of rocks upon pressure release, or even vaporization of the rock after pressure release. So for instance, if a rock has suffered a shock wave of 100 gigapascal, it will be entirely vaporized afterwards. That is the reason why we do not see meteoritic relics in large impact structures, because the bolide is completely vaporized. Yeah, you can see only geochemical traces of this material afterwards in melt rocks. Yeah, And the rocks will be melted at pressures exceeding 50 gigapascal approximately. Yeah, and below that, yeah, we have the typical field of shock metamorphism. Yeah, and there are some characteristic shock effects. Yeah, and they are so important for those who are studying impact craters, because they are our fingerprint to craters. Yeah, there is no other natural process by which these shock effects can be formed. Yeah? What I show you here, this is the only macroscopically visible shock effect. These are so-called shatter cones, yeah, from an Australian crater here. So you see, these are conical type of fracture surfaces with a typical striation pattern. Yeah, they're forming these subcones here on their, and everything is pointing towards an apex. Yeah, yeah. So, and the apex is pointing to the shockwave center. Yeah, so that is very important. If you find shatter cones in the field, yeah, you know you're standing in an old impact crater, even if you don't see the crater anymore. Yeah, because it's heavily eroded or so. Yeah, but there are even more important effects, but those are all microscopic effects. Yeah, we have different effects. Most of them are best developed in quartz. Yeah, luckily, quartz is rock forming mineral. You find quartz in many in sediments, in magmatic and metamorphic rocks. Yeah. And among the most important effects are so-called PDFs, that stands for planar deformation features. These are very tiny amorphous lamellae in the crystal lattice along certain crystallographic directions in the crystal lattice, where the crystal lattice has been became amorphous. Yeah, when the shock wave passed through this crystal here. And there are other effects like planar fractures, yeah, and so-called feather features. Yeah, these are all important shock effects. Yeah, yeah. Sometimes, yeah, it needs some expertise to really prove those effects. But if you find those features during your work, yeah, this is a very important indication for an impact origin. We can turn it around. No crater confirmation without approval of shock effects. Yeah? We need to find either meteoritic relics or shock effects in order to confirm a potential hypothetical structure as a confirmed impact structure. Yeah? So there is a specific procedure, yeah, to prove that. Yeah? So if you have some interesting rocks that may show these features, send me an email and I can have a look on it. Okay, so how do we know that these shock features form by shock waves and at which shock pressures they do form? Well, for that, we have carried out experiments for the last, let's say, 30, 40 years. Yeah, and a very important role in this respect plays the Fraunhofer Institute, Ernst Mach Institute, which is also located here in Freiburg. And they have facilities where we can reach really, really high velocities and where we can reach every shock pressure. Yeah, so that we can calibrate rocks. Yeah, so we are analyzing rocks. For instance, here you see a sandstone block. Yeah, in this chamber here, this is a bunker. Yeah, these are pressure sensors. Yeah, this material will catch the ejector. Yeah, here outside the bunker is a camera system, a high-speed camera with frame rate up to 10 million times per second, yeah, in order to record the entire process. And the projectile is being accelerated horizontally and reaches speeds here of up to 28,000 kilometers per hour. Yeah. So these are facilities of the Ernst Mach Institute here, and I show you one film that we did in collaboration with EMI, just to show you one of these impacts. I hope this works. It worked yesterday. Yeah. Yeah. So you see how this ejector cone is developing. Yeah. So the projectile came horizontally here. The target surface is vertical. Yeah. And you see the cone, which develops into a funnel. And here you see later spallation. Yeah. The entire film takes a microsecond or so. Yeah. So, and all the ejector is being collected in these catcher assembly here. Yeah, and the stress and the shock waves are recorded with these sensors here. Yeah, and we try to be as close to nature as possible. Yeah, as target material, we used a sandstone here somewhere from Germany. We characterized the sandstone with some porosity. We did different experiments. We filled the pore space with water. We looked at non-porous material, at porous material, and we used as projectile material real iron meteorites, yeah, and made spheres out of it. Yeah, this is a real piece of, or this is a real iron meteorite. We used Campo de Cielo that was found in 1576 in Chile. Yeah, and kindly we received a piece of it that we could use for these experiments. Yeah. So going back to our cartoon and the Reese Crater. Yeah? So that was the excursion to shock waves. So we have learned that the shock waves, they are able to create a deep cavity. Yeah? You see the cavity is growing and growing. There is not much remaining of the asteroid. That is due to when the shock wave is entering the free surface, it will be reflected as a release phase, which ends the shock front, yeah, or the shock phase, yeah, and well, eventually, yeah, we get a quite deep crater, yeah, which has this parabolical shape. It grows even further. We will see that at the end. Yeah, and yeah, you have seen these films where we can create those crater cavities experimentally. Yeah, and we can also do that numerically. Yeah, we try to validate the numerical models with the experimental craters. Yeah. For the students during our lectures, we also played with more, with less sophisticated models, yeah, using analog experiments. Yeah, here we worked with glass beads. Yeah, we colored the glass beads and fired with some 300 meters per second some bullets into it. Let's see if this. Oh, sorry, if this works. Yeah. Yeah, you see that a little crater has been forming, and interestingly, you see, yeah, this bowl-shaped cavity, and in the rim, you see that the strata is being uplifted. Yeah. Okay. Going back to the Reese Crater, this crater has reached a maximum depth. And reached a depth of about 4,500 meters. Imagine that, yeah, a hole 4,500 meters deep, yeah, and in diameter some 12 kilometers or so. The ejector curtain is shown here, and Above this cavity, we have a hot ejector plume that contains the vaporized material of the projectile plus vaporized material from close of the impact point. Yeah. Okay. So we can look in the Reese crater and in other craters to see what's happening during this phase when the crater is being excavated. Yeah, we call this phase the excavation phase. Yeah, and we see different things. Yeah, we see that while the crater cavity is growing, material is being injected into the crater walls. Yeah, we see dikes that are being injected. We see these wedges that are thrusted into the steep crater walls. And when the ejector curtain finally is landing, yeah, it creates this crater rim that is elevated, that is composed of this brecciated material, yeah, with inverse, which is overturned and has an inverted stratigraphy. And this material of the ejector curtain also, it is rushing outwards and producing some shear stresses to the target rocks, yeah, which show a radially outward type of movement. Yeah, so these are the structural aspects of the cratering. Yeah, we can nicely analyze these sort of things in small craters where the excavation or the bowl-shaped cavity has remained rather well intact, like Meteor Crater in Arizona. Yeah, this crater is about 1,200 meters in diameter with a nice museum here at the rim on the Colorado Plateau. You see the elevated rim, yeah, composed of ejecta. Yeah, here the ejecta is lying around. Yeah, and you see how the strata is being uplifted here in the rim. So the upper portion, this is ejecta. Yeah, and this is still the target material that is being uplifted to form this overturned flap. Yeah. The type of rocks that are forming during this excavation stage, yeah, are different types of breccia. Yeah. Crushed rocks, if they are composed of a single lithology, we call them monomict breccia. What we often see in the Reese crater, the deposits of the ejector curtain, these are so-called bunte breccia or polymict breccia, composed of the various lithologies that build up the target. Yeah, and if the ejector contains melted material, yeah, that suffered shock pressures of 50, 60 gigapascal and higher, then we call that suevite. Yeah? And the Reese crater is a type locality for this type of breccia. These suevitic rocks, they contain these melt lumps here in black. Imagine these black melt lumps, these were originally granites, yeah? But they were melted, yeah, due to the shock wave, and then later on got solidified and embedded in this clastic matrix. Yeah? And there is even a different type of breccia. Here it is opposite. The matrix is melted. Yeah? It's a melt rock, impact melt rock, and it contains differently shocked clasts. Yeah? All this happens at once at different sites within a crater. Yeah? These pictures are all from the Reese crater here. Yeah. So, but that's not all. I mean, for small craters, this excavation is the most important phase. And what comes next is of subordinate importance. But for craters like the Reese crater, this deep transient crater that has been formed, you remember this 4.5 kilometer deep structure, this is being modified. Yeah? And the deep crater floor is being uplifted to form a central uplift. The steep cavity walls are slumped into the crater, yeah, to form terraced rims, yeah, so that eventually the crater size increases, but the crater is not increasing in depth anymore so strongly, yeah, and it develops a sort of central rise, yeah, and these processes, they are triggered by gravity, yeah, and in particular, it is in particular the large craters that show these type of modification, yeah. We call this the third stage of cratering, the crater modification stage, yeah. You can see that quite clearly if we go back to the Moon and Mars, yeah. On the left-hand side, we see a simple crater, yeah. This looks quite similar to the cavity that has been formed after the excavation stage, with little modification, a little bit of slumping into the cavity, yeah. But here, there is a strong, severe modification. We have slump terraces, we have a flat floor, we have a central peak, yeah. So this is a complex crater, yeah. And the same type of features we do have on Earth. So at the upper panorama shows again meteor crater, which is considered a simple crater, still this bowl-shaped cavity. And the lower one, this is a complex crater in Jordan, yeah, not too far away from Turkey, in the desert, close to the Saudi Arabian border, yeah. It shows the crater rim, it shows an annular mode, what we call the ring syncline, and a central uplift that is peeking out. For scale, you see our Jeep here. Yeah. This is a 6-kilometer complex crater called Jabal Waqaf Suwan, if I pronounce that correctly. Okay, so you see there are remarkable differences between simple craters and complex craters, and you can express that quite nicely when you compare or when you determine the ratio of depth of the crater to the diameter. Yeah. So these simple craters typically have a ratio depth to diameter of about 0.2. So the diameter is 5 times larger than the depth. Yeah. But here, at this point, the slope suddenly changes. The depth to diameter ratio changes about to 0.1. Yeah. That means the depth is only 10% of the diameter. Yeah. We call that the simple to complex transition, yeah, of crater formation. The lunar database is much better than the Earth database, yeah, which you can see here. Yeah. But still, it shows approximately the same, except for the circumstance that the simple to complex transition on the Earth is at about 3 kilometers. Yeah, so craters less than 3 kilometers are simple craters, larger than 3 kilometers are complex craters. While on the Moon, we have this transition at about 15-kilometer diameter. And this shift is a function of the gravity. On Earth, we have a gravity 9.81 meter per second squared. On the Moon, only 1.6 meter per second squared. Yeah. Okay, and this crater modification can also be nicely shown here in numerical simulation. This is a numerical simulation by Kai Wünnemann, a colleague of mine from Berlin, Museum of Natural History, and it shows the initial collision. Initially, you form the deep cavity. Yeah. Oh, sorry. Oops. Sorry, let's do it again. The deep cavity is forming, and then the floor is rising to form the central uplift. Yeah. And all what is in red and orange is the damaged crater floor. Okay. So I'm a structural geologist by training, with a standard background in geology, and I've studied quite a few complex impact craters and came up with this type of synthesis of inventory of complex craters. Yeah. So you see at the rim, you see this terracing. Yeah, these normal folds are developing into, they sometimes have listric shapes, develop into detachment, low angle normal folds. Yeah. But what is typical, or what is important in impact craters, is when you have this collapse of the crater formation, everything is crowded towards the center. Yeah, you have the downslumping towards a single point, and you get a space problem. You do not have plane strain deformation, but you have constrictional deformation. Yeah, so you have a space problem, and that leads to some type of folding or formation of flower structures. Yeah, in radial orientation, and I show you some of these structures in the real world. So this again is a Reese crater showing this typical terracing by normal folds. This is a crater rim, and then we see multiple normal folds, some with listric shapes and antithetic rotations. Yeah. And in other craters, yeah, this is a crater on the Colorado Plateau, one of my favorites, upheaval dome. You see this space problem, yeah, because everything is crowded together during inward slumping. You start to form radial folds. Yeah, these radial folds. It is like if you have a blanket, or and you lift it up. Yeah, it forms these type of folds. Yeah, they plunge outward the fold axis. Yeah, so the center of the structure is somewhere here, and you see nicely these radial folding. Yeah, this is here from the periphery of the central uplift of this crater we have seen before. You also see this nice folding in the periphery of the central uplift here. Yeah, very beautiful. So you can really do structural geology in these craters. This is what you know as a flower structure, which typically forms in restraining bands of strike-slip folds. You know these positive flower structures, transpression ridges. Yeah, but these sort of features also form in radial orientation in craters. Yeah, because of this convergent flow field. Yeah, this is from a investigation of a crater in Australia called Matt Wilson. And the funniest and most complex structures we see occur in the very center of the central uplift. This doesn't look like what you expect a crater should look like. Yeah, this is the spider crater. This is just a central uplift. Yeah, and it is a remarkable feature. Tectonically, it is this. Yeah, you have a multiple repetition of thrusts, yeah, an imbricated stack of thrusts, yeah, that surrounds a center, yeah, and it shows some symmetric elements. Yeah, sorry. This is a typical type of deformation that happens within a central uplift of an obliquely impacting crater. Yeah, so you have a preferred transport direction, yeah, in downrange direction, yeah, but very complex tectonic setting. Yeah, even more complex is the structure here. This is the central uplift, very well exposed in this crater upheaval dome. Yeah, this is a central uplift, and what's happening when you have this convergent flow? Initially, you form this radial folding, but eventually these folds get more and more and tighter. One limb is sheared off, and you get reverse folding or thrusting of different slices onto each other. It's like the closure of an iris of a camera lens. Yeah, and yeah, this happens here. We try to reconstruct the structure in 3D following one single horizon. Yeah, and this is one single horizon that we constructed, and you see how complex it is folded and folded, yeah, within the central uplift. I really like central uplifts because of their complexity. And these are the results of a few mappings of central uplifts of some of the craters. This is the Jordan one, also very complex. Yeah. This is the one in Utah. This is a Spider crater, and this is Matt Wilson. It shows the complexity of geologic structures here in the core of these complex impact structures. So now my shortest chapter starts, defense strategies. So what if one of the near-Earth asteroids is on collision course? Yeah, do we have any defense strategies? Well, first of all, we should know what happens. Yeah, and just to show you the effects of a bolide of 100 meters diameter approaching the Earth, what type of effects could we expect? Yeah. The energy of such an event would be in the order of 75 megatons TNT equivalent. The probability of such event is every 1,000 years, once, somewhere on Earth, not in Istanbul, but the crater size would be 1,500 meters in diameter, so similar to meteor crater, with a crater depth of about 350 meters. The ejector would form a continuous blanket with a radius of about 5 kilometers. We could expect seismicity in the order of a Richter magnitude of 5.3. A lot of damage would caused by the air blast and the burning. Yeah, we would have 1.3 bar overpressure at 10 kilometer distance, 250 kilometer per hour wind speeds. For such an event, we can expect a lethal zone with a radius of about 20 kilometer. Yeah, for such an event. So for a 100 meter asteroid, yeah, if the structure is even bigger, the bolide, let's say 1 kilometer in diameter, let's have another impact at the Reese Crater, exactly where the Reese Crater has been formed 15 million years ago. What would be the environmental damage? Well, so the Reese Crater here in southern Germany, so for scale, this is the River Rhine, here's Frankfurt, here is the coast. Yeah. So Munich would be somewhere here, and Nuremberg somewhere here. And so this is a range of expected blast. Yeah. So the blast would reach some 500 kilometers radial distance. Yeah. So wood houses would collapse in a radial range of 300 kilometers. Brick houses would collapse in a range of about 250 kilometers, and steel-framed buildings would collapse in 200 kilometer radial distance. Or no, yeah, what is it? 100 kilometer radial distance. Yeah, a similar radial range occurs for the thermal radiation by the impact plume. Yeah, so everything is burned here in this reddish and orange areas. Yeah, you have 30-degree burns. Yeah, in this range. Yeah, up to some 300 kilometer distance. Yeah. In terms of seismics, yeah, well, the magnitude of a Reese impact would be a magnitude of 10. And well, but in comparison to the thermal radiation and the air blast, the effect is less severe. And the distribution of ejecta is also much less severe than the effect of the air blast and the thermal radiation. So in conclusion, if such an event would happen in southern Germany, the entire half of Germany would be completely destroyed. Yeah? But this is still a regional effect. Yeah? It needs even bigger objects, yeah, to have a global global catastrophe. Yeah. So, but the damage is extreme. So we have to think about what can we do against this. NASA and ESA are working on that, doing experiments, and now also doing a mission to understand that. Among the options is a sort of kinetic impactor, where a heavy spacecraft is rammed into the asteroid that is on collision course, or you make a sort of explosion close to the asteroid, and then the blast will likely deflect the asteroid. You would not try to fragment the asteroid, because then it is no more predictable what happens. Yeah. I told you there is a mission ongoing, the DART mission. It's a concerted approach by NASA and ESA. At the moment, the NASA spacecraft is on its way to this moon, to this asteroid, Didymos, which has a little moon. Yeah. And this spacecraft, which is on its way to Didymos and its moon, will be rammed into the moon, and a little second spacecraft will be measured the deflection. And then shortly afterwards, the European ESA mission will come and will measure with high resolution what really has happened in this asteroid that has been rammed. Yeah. So this is a real scenario that is now on its way, and you probably hear about it in the news when it's going on. Yeah. Another scenario is that of a gravity tractor. This is less spectacular. A massive spacecraft is parked right next to the asteroid. Yeah. So two masses attract each other, yeah, in both ways. So this massive spacecraft also attracts the asteroid. Yeah. So, and if the asteroid, if the spacecraft is moving away, it potentially can slightly pull the asteroid as well. This is probably wishful thinking. This has never been tested, but these are the ideas. Okay, and now this is my last slide for today here. So I hope I could convince you that impact events are among the most fundamental processes in the solar system. This is not my sentence, it's the sentence of Gene Shoemaker. This is, let's say, the grandfather of modern impact research. Yeah? And yeah, we have seen that the Earth's atmosphere provides a good protection shield against smaller objects up to several decameters. But when these bolides become larger than a few decameters, then real craters form at the ground. Yeah? So, and real craters form in periods of 100 to 1000 years. And of course, we have seen the statistics. The very big craters form only very rarely. Yeah, thank you for your attention.
Thank you so much, Thomas. It was a really nice talk. We can start with a small discussion and get the questions. Let me check, and if the arkadaşlar da bana yardımcı olabilirse soruları alalım. There is one, Hüseyin Akkuş, I think bir şey sormak istiyor. I think he wants to ask something. Yeah.
Can you hear me?
Yes?
Yeah.
Because I don't open my video camera. I'm a board of member in the Chamber of Geological Engineers. It was really impressive presentation for me, and also I learned some new information about asteroid impact, especially shock waves, fireball, air burst. Therefore, I would like to say many thanks for sharing your experience with us as the Chamber of Geological Engineers. It was really impressive presentation, and it's also so clear for me. Thank you so much, Thomas. I don't have question, by the way.
You're welcome. Yeah, it's a pleasure
we will host you again in the future. And we are also seeing you new topics, because it's really interesting topics for us.
Thank you so much.
Thank you, Thomas.
I just want to add something to beside of that. It's really important to knowing the new different multidisciplinary works also, and impact cratering is not that common in Turkey. We all know that, and we don't have the only planetary institutions, or some institutions maybe roughly talking about the impact cratering process, but I believe it's really important for also the other geologists who is working on the field, like I don't know, maybe for companies, the mining companies, or structural geologists and other geologists, whatever. If they went to the field, they of course looking for different kind of the rocks. They're seeing the formations, and if someone is realize that is related with the impact events, is a huge finding for this impact community. And that's why the transporting that kind of information from the scientists to the local people or the normal geologists working for the companies is really crucial. And that's why I would like to say also thank you again one more time, Thomas. And I have a one maybe cozy question. What's your favorite crater so far you have been? It's really tough, I know, but...
Well, the interesting thing is impact craters, I mean, they are so destructive, but the remains of impact craters, they are so nice that it is really fun to work geologically in it. Yeah, you can work with the tools you have as a standard geologist. You can apply that. You can do structural geology, you can do geophysics, you can do everything in impact craters. And of course, some form extremely nice landscape, like Upheaval Dome, what I showed you, yeah, because it's so well exposed. And of course, these Australian craters, I have studied a few of them in the outback, where I was brought with helicopter into the center of the structure, working there for 3 weeks, and then I hope that the helicopter came back. Actually, yeah. And so it was. These are personal experience with some areas, yeah, and yeah. But each of the crater is unique in itself. I tried to present some common features, but each of the crater also have their personalities. Yeah.
Okay. I think there are some questions. Cemal Tunoğlu, let me wait a second. You're still muted, and I give you permission. Arkadaşlar Cemal Bey'in
Cemal Hocam istek gönderdim size. Sesi açabilir misiniz?
Okay, thank you very much. Thank you very much for your interesting and good presentation on the important impact asteroid.
Thank you.
I wonder, you didn't mention on the shock quartz, iridium anomalies, and boundary clays, or impact clays. You know that important geological impact material, all of these. And you didn't mention about this.
What do you mean?
Shock quartz,
Yeah.
iridium anomalies, and boundary clays or impact clays.
Okay. So I was talking about shocked quartz. I presented these planar deformation features, planar fractures, and feather features that are typical in quartz. So quartz is really the important mineral. And for instance, the Reese Crater, until the 60s, the 1960s, it was considered as a volcanic feature. Yeah. And it was the finding of coesite and stishovite, the high pressure polymorphs of quartz, that changed the situation, the paradigm shift. Yeah, that it is. So these high pressure polymorphs, yeah, you're right. I did not mention those. They are not only occurring in quartz. Also, for instance, if you have carbon-bearing material, you produce diamonds. Yeah, or if you have olivine-bearing rocks under shock, you can produce ringwoodite. Yeah. So these phase transformations towards high pressure polymorphs can happen. Yeah. And also in clay rocks. In clays, it is more difficult. Clay material, you know, it contains OH groups. We did some experiments with clays. It starts to dehydrate the OH groups. It develops bubbles, and kink bands develops previously, but kink bands in clay-rich or mica-rich rocks also form under tectonic forces, as you know. Yeah. So quartz followed by feldspar are definitely, I would say, the best minerals to prove shock. Yeah. Is that
yes
of the answer? Yeah.
Yes. Thank you very much.
Ersan Hocam soru soracak galiba. Onu da bir
Tamam,
sırayla alalım. Arkasından da Hasan Bey'i alalım.
Tamam. Hi, Thomas. It's nice to see you
Hi,
again.
Yeah.
It was a really nice presentation. I really enjoyed following it. It was a good introduction to the concept, and it's nice to see you again, really.
Yeah.
So I have
Thank
a question actually related. It might be a little bit out of your interest or maybe your subject, but somehow you have shown mostly examples of inland structures, actually, impact on inland and the geological results of them. Do you know any examples of records of a crater or a meteorite in soft sediments, in the marine sediments or lakes? Because, for example, for earthquakes, we study seismoturbidites. These are records of earthquake, of the shaking of the earthquake, and they can be followed in the soft sediments in a marine environment. Do you know any instance of any examples of such a record for meteorites?
First of all, there are a couple of craters that formed, for instance, in shallow marine environments. For instance, at the east coast of America, of North America, the Chesapeake Bay crater. It's a large buried structure that formed in soft sediments of the passive continental margin. And this, an ICDP drilling campaign has investigated the structure in great detail with forceful research of sediment-laden water came back to fill the cavity. There are other craters in Sweden, for instance, the Lockney crater, and some others that show these soft sediment type of deformation. And concerning the seismites, these soft sediment convolute bedding type of features, this is interestingly known for the Reese Crater. Yeah, you know, the Reese Crater formed 15 million years ago at the northern shore of the Molasse Basin. That was a foreland basin to the Alps. It was, at that time, it was not marine. It was the upper freshwater Molasse period, but there was high standing water. So at least the water, the sediments were water saturated. Yeah, and we do see in these environments, probably fluvial environments, or we do see some 50 up to 150 kilometers away from the Reese Crater horizons with seismites.
Yeah,
yeah,
that's interesting.
And these are getting several meters thick. They are connected to dikes, sandstone dikes, sand volcanoes, yeah, and then this tremendous convolute bedding, yeah, and also associated with horizons of shocked material, yeah, of distal ejecta. Yeah, so the connection to the Reese Crater is clear. Yeah,
I see. So we should be careful actually when we interpret seismites as earthquakes all the time.
Well, these are impact-induced earthquakes.
Yes, actually, yes. Of course.
It is a question whether the characteristic of these earthquakes is similar to that of endogenically triggered earthquakes.
Mm-hmm. Yeah, I see.
Yeah.
I have one more question about the impact probability. Can you a little bit explain the the data for the statistics there?
Yeah.
The impact probability you showed the graphic.
Yeah.
What is the input there?
Yeah, the input is has different sources. The first and main source is what we know from the moon. Mm-hmm. Yeah, moon. We have the complete crater record, and due to sample return from the Apollo missions, we could date some regions which have a certain crater density at its surface. Yeah, and this we could calibrate. So we could say, okay, if we have a certain crater density that dense, this has the age of this billion years and so on. They did it at several places, and this gave a fairly good chronology that is now used as the main tool to do stratigraphy in the solar system. So sedimentology, or when you do stratigraphy in terms of planetology, you make crater counting. Yeah.
Yes.
The higher the crater density, the older the exposure. Yeah. Mm-hmm. So that is the principle, and this was adopted to the Earth, and then additional sources like, for instance, the population of near-Earth asteroids, or the influx of shooting stars, or the craters we see on Earth. All this comes into this statistical approach, but it is not good as it may look like. Yeah, so we need to elaborate on that.
Okay, thank you very much.
We are currently running or trying to foster a project where we exactly try to get more precise prognosis, yeah, of the impact probability and also the environmental impact. Yeah, I showed you some results, yeah, but it is in detail much more complex. Yeah.
Of course, it's okay. I was just wondering. Thank you very much.
Yeah.
See you. Hope to see you soon.
Yeah.
Ciao.
Ciao.
Okay, we can move Hasan Bey.
Evet, sesim geliyor mu?
Evet, diyoruz. Yeah.
Thank you very much, Thomas, for your informative presentation. I have a few questions. If Oğuzcan can give permission to me, and if you have time, I'd like to discuss this questions with you. And the first one is why we don't have heavy bombardment present day. Is it possible to start again? What is the reason now there is an unbalance? And is there anything to disorder this balance and start again?
Oh, the early and late heavy bombardment was due to some orbital shifts, Jupiter and Saturn, which caused some disturbance in the asteroid belt. Yeah, and the early heavy bombardment is, let's say, the tailing end of the accretion history of the formation of the solar system itself. Yeah? And the late heavy bombardment is due to an orbital shift of Jupiter and Saturn and Uranus, yeah? Which caused a lot of chaos in the asteroid belt, yeah? And which pushed a lot of asteroids into the inner solar system. Yeah? Mm-hmm. I would say this cannot happen anymore. Yeah? What principally can happen is that a major collision event within the asteroid belt, yeah? And that can cause for quite a while a larger population of bodies that are entering the inner solar system that may lead to an enhanced period of collisions. Yeah, so that is something that I would not exclude. But we see on average, if we look in the past 3 billion years, this levels out quite nicely, and we see the major refilling of the near-Earth asteroid population is due to infalling asteroids into these Kirkwood gaps, yeah, which then become near-Earth asteroids. Yeah, so it's a sort of balance, a sort of equilibrium that is reached.
Okay, thank you. So another one, the second one is, it's thought that they brought water as a frozen into the Earth, and so we have water on the Earth. So why we don't have in the other planets? They had under bombardments, and they brought water, but we don't have water on Earth, on Mars, and other planets, on asteroids, for example.
Yeah.
So can we say that the meteorites are not only source of the water of the Earth?
Well, that is indeed a scientific question. When we look at our orbital range of the Earth, we wouldn't expect primarily so much volatiles on Earth. Yeah, so the idea came up that most of the volatiles and also the carbon came, for instance, by chondritic projectiles, by carbonaceous chondrites, by comets, cometary material, as you said. And well, this should also have happened for other bodies, yeah. And the question is, can those bodies keep the water? Yeah. Yeah. This is a function of gravity, of course. Mars has a lot of water. Yeah. Most of the water is now in the ground. Yeah. And but Mars already lost a lot of water. Yeah. In the early period, yeah, when it was volcanically more active, there was an ocean in the northern hemisphere. Yeah. But a significant amount of these volatiles could escape from Mars because of the lower gravity. And
evaporation is another reason.
Evaporation, of course. If you go to Mercury, you have due to the neighborhood to the sun, you have so strong heating and cooling, depending on if you have the day or night time. Yeah, so that you have strong vaporization. Yeah, and blowing away of the material. Yeah, so Mercury couldn't hold it. Yeah, and Venus Venus is supposed to be a rather dry environment. Yeah, it has a high CO2 concentration, which creates this glasshouse effect. Yeah. Yeah, this is a good question. Where the water has gone. Yeah.
I can add something, Thomas.
Yeah.
Also in the moon, they just found out recently it just trapped under 3.1 to 4.2 kilometer depth. Because it's unstabilized with the surface pressure, it just penetrates towards the inner. And most of the water is also coming from comets, but some little amount of that is also related with the moon formation itself. Because initially it's also another story, but there was another kind of the body just to collide to the Earth, and it's also getting one piece of it. And they thought some little amount of the water is also just extract.
Sure. This depends on the formation of the moon itself. And of course, initially the moon was considered as completely dry, but it is not.
It's not, yeah.
In the South Pole area, for instance, they detected water. And of course, for Venus, we have, due to this tremendous glasshouse effect, we have temperatures of 400 degrees in the atmosphere, and atmospheric pressure of 90 bars, where water is not stable. Yeah.
Okay, Thomas, you showed us a very good map showing the crater locations on the world. And there was some big ones like in Chicxulub in South Africa and in United States. So we know what happened in Chicxulub, but we don't know. I didn't know what happened in South Africa and United States. Do you have any traces for them? For example, ash level or some mineral enrichment in the levels, and burnt plants materials in the levels. Do you have? And do you see? Do you hear anything about them?
Yeah,
when we look as big. In United States and in South Africa, in your map, they are as big as the Chicxulub collision.
Yeah, they are even bigger than Chicxulub. Chicxulub
really?
Is at 180 kilometers in diameter, and Vredefort Vredefort is 250, and Sudbury also larger than 200 kilometers in Canada. The problem with these two, they are 2 billion years old. Sudbury is 1.8 billion years, and Vredefort is 2.03 billion years old. Yeah.
Interesting.
Yeah. So this has been gone, and what we see from Vredefort nowadays is we are looking at the deep ground under the original surface. So
by seismic
upper 8 kilometers, yeah. So we have erosion by 8 kilometers, yeah. Only the root of the central peak, yeah. In case of Vredefort, yeah. Yeah, that makes it difficult to of course to see some environmental impacts, yeah, as with Chicxulub, yeah. But what we do see in the Archean is we see beds, for instance, in the Barberton Mountain land, yeah, quite nearby, spheral beds, impact spheral beds, yeah, that are forming as response to huge impacts. Probably not the Vredefort impact itself, but other impacts that we have not discovered yet.
I didn't know their times. They were been very old, 1.2 billion years. At that time, there was no any life, just initial life.
Absolutely right.
3.5 billion years ago. So we don't see any extinction because of
No. Absolutely right. Yeah.
Thank you.
Hasan Bey, sorunuz bittiyse bir tane de there's one question in the chat, Thomas. I would like to translate for you.
Okay.
Hussein Alan is asking for Has Germany conducted nationwide risk analysis for asteroid impacts? And maybe in addition to that question, I would like to also ask how we are ready to the possible impact scenarios. If you can briefly maybe introduce what is next for European disaster project or something like that.
Okay.
Oh.
Yeah, I briefly mentioned that already. Yeah, we should ask ourselves: are we prepared? Are we prepared for any type of catastrophe related to impacts? Yeah, I mean, both in terms of probability, what should we consider most? Yeah, what is probably more unlikely, and do we have any plan what to do then? Yeah, and indeed we are right at the moment. We have next week a meeting with the German Research Foundation, yeah, and a meeting with people from all over Germany, sitting together, and we try to convince the DFG that they finance a sort of consortium of people who are looking not only at the crater process itself, but also at potential environmental issues. Yeah? What is the effect of blast on trees? Yeah? What is the dimension of impact-induced earthquake damaging? Yeah? What is the impact on heat radiation on these things? And there are also people on board from social sciences. Yeah, they are, and also looking, and also engineers looking at how robust are cities and infrastructures. How robust is energy supply and the economy when these scenarios of certain sizes happen? Yeah, I mean, we are living in a phase, in a period where we are facing a number of very critical situations. Yeah, like yeah, of course, the most severe one is the climate crisis, of course, but also the war in Ukraine. We are facing that things are getting unnormal. Yeah, and in this period, we should think in terms of such events that they can indeed happen, and that we should be prepared somehow.
Yeah, but in terms of the question again, there is nothing happened so far to analyze the risk of impact events from the Germany side, isn't it? Or is there any map?
A certain event that is likely to occur?
Yeah, it's like a risk analysis map or something like that.
Okay.
If it hits to Berlin, what happens, and or something like that, or München, or no. It didn't happen. So
this is not existing, and if you look at the known near-Earth asteroids, their close encounters, this you can check daily in the internet what the closest approaches are, and how likely it is that some bolides are colliding with the Earth. At the moment, there is no danger from any of these known asteroids. However, we know from the Chelyabinsk story, this can happen out of nothing, because we don't know the entire population of near-Earth asteroids.
Also, it depends the size of the projectile.
There is a certain remaining risk for the asteroid Apophis. You may have heard of it. This is a 350-meter diameter asteroid that comes very close to the Earth in a couple of years, I think in 2029, in 8 years. And then again in 2036, it comes as close as 30,000 kilometers to the Earth. That is closer than some of the satellites orbiting around the Earth. But for these first two encounters, we are safe, but it depends on the behavior and the talk of the asteroid. If a future encounter, in particular in 2068, could cause a collision. Yeah, so at the moment, they cannot exclude by 100% that this bolide could not collide with Earth in 2068.
Okay.
But the chance is very small.
Okay. Hasan Bey Hasan Bey bir şey sormak istiyor. Bir saniye size arkadaşlar. Ben verdim.
Vaktimiz var mı Oğuzcan Bey?
Bir iki soru daha alabilir, sonra kapatalım. Let's say the last two questions and we can just...
Başka kimsenin sorusu yoksa?
Göremiyorum chat'te şu anda. Buyurun Hasan Bey, sizinle bitirelim.
Sorry Thomas, here I am again. Shock-related fabric, metamorphic fabric. Do you have any information about the difference between the regional metamorphic fabric or contact metamorphic fabric and shock metamorphic fabric? How can we separate them?
Yeah, it looks completely different, absolutely different. Yeah, there is no field of overlap in terms of pressure and temperature between regional metamorphism or contact metamorphism and shock metamorphism. You know, metamorphism is a sort of equilibrium. Yeah, you produce new phases that are in equilibrium to the certain PT conditions, and so shock metamorphism is disequilibrium. There is no equilibrium because
suddenly it's happening.
In this short period of times, you cannot reach a thermodynamic equilibrium. Yeah, and the structures look entirely, completely different. Yeah, there is no chance of puzzle these two.
Okay. Do you have thin section about that?
Million.
Oh, I like to see them, but
yeah. Well,
you can share some picture.
As I told you, when we want to prove an impact crater being of impact origin, we have to document shock. We have to document shock to the impact community, yeah, in a convincing way. That is, you need to take samples. You need to prepare thin sections. You need to document, for instance, the crystallographic orientation of these planar formation features and all these. There is a certain procedure what you have to do, and this is, yeah. So at the end, there is a great agreement in the impact community of what is an impact crater and what not. Yeah? So that the criteria are quite clear, and there is no way of puzzle endogenic metamorphosis and impact metamorphism. Yeah.
Do you know any document about it, a book or something, paper? How can I maybe I can reach?
Yeah,
digital library.
I mean, if you put in Google Scholar, shock effect, you will find
basic question, Thomas.
Yeah.
And is there any key to separate normal sinkhole in thick alluvium and crater? Basically, very basically, if you visit somewhere, you saw a hole, and what is the first insight? It is a hole or crater?
Yeah,
basically,
this is not easy. This is not easy, and in terms of morphology, of course, a crater. If you form a little crater pit, yeah, of course you have a raised rim, you have breccia, yeah.
Yeah, of course. I understood very, very well. You told us the internal structure, but if you look at from far and you are going toward the hole, and how can you separate if it is a hole, or is there any key?
Well, I cannot say right from the beginning what it is. Yeah, it is. For instance, I give you an example. There is a group of German researchers that postulated a lot of impact craters in southern Germany in an area formerly covered by ice, the Piedmont glaciers, yeah, and there are these dead ice holes. I don't know if you know these features, that are circular holes, yeah, like kettle holes, and these are dead ice holes. So they have a completely different geomorphologic formation, yeah, but they claimed these are impact craters, yeah, but they did not give the critical proof, yeah. For those small craters, it is usually meteoritic material that you find, yeah, and you really have to document shock, otherwise you cannot call it a crater, and that is what many people are not understanding and not doing, yeah, yeah. But related to this, I have a question to you, to all of you, yeah. I mean, you are the expert, and so far we have not. We have no proven craters from Turkey. Yeah, there should be a lot of craters there. Well, it is. There is a lot of tectonic ongoing in Turkey, obviously, and we have alpine orogeny, high erosion rates, and all this is probably not very likely to find craters, but they could form there, of course. And I'm wondering if some of you have found some, let's say, anomalous breccia that you cannot explain in terms of the tectonic environment, or if you, when doing geophysics, seismic surveying, if you have some suspected structures that you cannot explain with tectonics, with sinkholes or these sort of things. Is there anything like this?
When I saw the map, the crater world map, I was upset because I didn't see any impact in Turkey. So it was clear, but as you say, possibly it is very tectonically very active in a very young orogenic belt. Maybe it could be, of course must be, but we don't have any trace so far. I don't know. But be sure, this will be my next job, to look at very detailed if there is or not when I go to field, if I see any hole, any something like that. So I will look at it, but I don't know exactly if there is or not. Maybe because of the active tectonic area. Do you? I don't remember on the Alpine Himalayan orogenic belt if there is any impact or not in your map.
Well, we have a few craters in orogenic belts. Some are even overthrusted. For instance, in the Caledonian orogeny, we have two craters, Ridland and Lockney, that have been overthrusted and later being exhumed. In the Alpine orogenic belt,
I don't think so.
No. There's one, Karakul, the Karakul structure. Yeah. This is, where is it? In which part? In Kyrgyzstan, I think. Yeah. This is a crater so it's more difficult to find them in regions that have a higher erosion rate and that are tectonized. Yeah. But I would say it's not impossible. Yeah. But I found it in my career quite, and some of them by chance. Looking, for instance, the structures in Saudi Arabia, collaborating with people from Saudi Aramco, yeah, which have deep seismic sections, yeah, and they were wondering, well, they're looking for hydrocarbons, Yeah, and they are not interested so much in the structures, how they formed, but luckily enough, I got in contact with these people, and by this we could confirm some structures in there. Yeah, and so it's sometimes just a curious history of circumstances that leads to a discovery.
Yeah, maybe because in Saudi Arabia, because it is a shield, very old shield, and covered by younger sediments. The younger sediments, maybe as you show on your graphic, maybe covered, buried, and you can find it. But here, I think in tectonically active area, maybe disorder, maybe clean, maybe under truss. We don't know. Maybe happened, but unfortunately, we don't have now. I don't know. Sorry.
Okay, there is one and the last question.
Thank you very much, Thomas.
From chat. Ridwana Hassan is asking for this in 2029 asteroid that will come near to Earth. Is there any chance that it could be changed? How closeness it will be the Earth?
No, for 2029, it's the path is very clear. Yeah, and it has been calculated. Well, the uncertainty of orbits that are calculated to the future depends on how long these asteroids have been mapped and observed. Yeah, and this asteroid is under very close observation. Yeah, so they know very, very precisely the path, and it's absolutely safe that this will that this close flyby will be at about 30,000 kilometers. Yeah.
Okay. I would like to say thank you again, Thomas, and teşekkürler herkesin katılımından dolayı çok teşekkür ediyoruz also. Jeoloji Mühendisleri Odası'na da buradan teşekkür etmek istiyorum. Özellikle arka tarafta bu yayının yapılmasını sağlayan, yardımcı olan arkadaşlarımıza çok teşekkürler. Bir sonraki oturumda belki yüz yüze bir şansımız olursa görüşmek üzere. O zaman bitirebiliriz.
I would like to say thank you for